This YouTube is about programming with pointers. Not the pointers like, you know, this kind of pointer, but programming pointers. The examples I'm going to do in this YouTube are complementary to what's in your textbook, although I will do some of what's in your textbook as well. Okay, so moving on. Before I talk about pointers, I want to talk a little bit about memory concepts within your computer, because that will help you to understand what the pointers are doing. So in your computer you have your central processing unit, your microprocessor, right? And in memory somewhere in RAM or ROM you have where your program resides. And each statement of your program or each data element of your program is converted into binary and stored in a location in memory. And it's in binary, so I show it in binary. So whether it's an instruction or a piece of data, it's stored in memory. And your CPU has to go out and fetch that instruction or that piece of data, bring it into the CPU, process it, and then return it to its place in memory, or go on to the next instruction in memory, as the case may be. This is a whole course in itself. It's a course in assembly language, understanding how all of this works with your microprocessor and your memory. But the main thing I want to point out about it is that your program resides in memory somewhere, and each memory location has an address. Same with your arrays. Each element of your array has an address associated with it, because each element of your array is a piece of data and it has an address in memory. The CPU has a thing called a program counter, which keeps track of where what address it's in memory. So it always has to keep track of, get this first location out of memory, bring it in, get this next location out of memory, bring it in. And in the meantime, this program counter is keeping track of where it is in memory. There's a link down here to illustrating this whole fetch and execute cycle in a microprocessor. If you are interested in that more, one, take a course in assembly language. Two, go ahead and go to that link and take a look at it. It's a nice illustration, but you really have to spend some time with it. So before we go on to pointers, I'm going to point out to you that we've already been dealing with addresses in memory, whether we realized it or not. And in particular, we've been using the address operator, which is this ampersand. We used it when we used the scanf function, because basically it says get a value, read a value from the keyboard and store it at the address specified by ampersand x, or the address of x. So you get a value and you store it at the address of x when you use the scanf function. And I have an illustration to prove that point here. I've declared two characters right here. One's an ampersand and one's a number 2. That's my phone ringing. Sorry, I was momentarily distracted. When I hear my phone ring, it distracts my train of thought, so I shut it off. Okay, so here's my example. I just took off the color so I can illustrate things now better as I go along. So my example of showing the address operator that we've already been using, I have 2 character variables here called A and B. One of them the value is an asterisk and one of them the value is a 2. So my first printf statement, I say I want to show what A is, and it's a character, so I use the character format specifier here, and sure enough A equals asterisk, no problem. But then I also say show me the address of A, so the ampersand A, show me the address of A, and my format specifier is %x, which means it's going to show it to you in hexadecimal. So address of A is, there it is. It's a hexadecimal number, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Hexadecimal. My assumption is that you already have some familiarity with hexadecimal. If not, you really don't know what it is, please send me an email so I know. Okay. My next printf statement says B equals, and instead of saying character, I used a decimal. Base 10, in other words, base 10 format specifier, and there's B. So when I do that, I'm actually going to, it says B equals 50. Why does B equal 50? Because 1, I didn't express it as a character, and 2, it's showing me the ASCII value. So the ASCII value corresponds to 50. So what's actually stored in your computer for this character 2 is the ASCII value of 50. Now, if this had been an int, it would have stored it as a 2, but I stored it 2 as a character, which corresponds to the ASCII value of 50. And your Windows calculator has a mode called Programmer, which is kind of neat. And I can, for example, I said 50 decimal, right there, I'm in decimal. I can show you what that is in binary. There it is in binary, so it's 0010. There's leading zeros here, so we get one whole byte, because a character takes a byte to store it. I can also show you what it is in hexadecimal. So your Windows calculator in programmer mode is kind of nice because you can go between these numbering systems in a computer, in a programmer world. So number 2 has been stored as a character, which has an ASCII value of 50 in decimal. And then I said, what is the address of B right here, right? What is the address of B? And I want to store that answer as an unsigned int, or I want to display that answer as an unsigned int. So instead of displaying the address as a hexadecimal address, I displayed the address as a unsigned int address. But the point is really that that all along we have been using this ampersand, which indicates a address. So now let's go on to pointers. Pointers are variables that can store addresses, and I have an example to illustrate that. So I have a number, an int number, whose value is 99. So 99 is stored somewhere in memory. So I put 99 here, stored in memory. Its identifier, which is the name we've given it that our program can use, is called number, and it's stored at some address right there, and I've made up that it's stored at this address supposedly. Okay, and now I'm going to declare a pointer, and I'm going to go over this notation in a minute, but this is called a dereferencing operator. So I say that the address of number, remember the ampersand means it's the address of number, I'm going to store it in a variable called p number. And by putting an asterisk in front of it, that indicates I'm storing a address here. So the value of the variable p number is the address of number. And I'm going to show that to you here. So p number gets the address of number. So this is the address of number right here, and I'm going to give that to p number. So p number, that's the identifier, is storing this address, which is the address of number, whose value is 99. But p number is stored in its own location in memory, so p number has its own address, which is right here. So that's what's happening. So let's talk a little bit more here. Okay. So declaring pointers, you declare a pointer with an asterisk in front of it, in front of the variable name. So the variable with the name p number is a type int with an asterisk at the end. Even though in a moment, by the way, I can see the asterisk here is next to p number. You can also declare it like this, int asterisk p number. But the point is that I am saying that p number is an address. Otherwise, it would be an ordinary variable name called p number. But if I put the asterisk in front of it, I'm saying I'm storing an address. P number can store any address, or it can store the address of any variable of type int. It's very important that we match the data types with the pointers pointing to the data types. I'll show you more in a moment. You must initialize your pointer. Uninitialized pointers are very hazardous to your program because you've made a pointer, and if you don't initialize it, it's going to be some arbitrary address, and you can really wreak havoc in your program because it's pointing to somewhere you don't have any control over and you don't know where it's pointing. So always initialize your pointer. If you don't know what to initialize it to null just to be safe. So the compiler has to know what type of data is stored into the in the variable that you're pointing to, so it knows how much memory in bytes that the variable is going to occupy. So an int, for example, takes 4 bytes on my machine. It can vary, and it can be within this range of values. We showed that a little bit when we were using size of in my last YouTube, but I'm going to show a whole lot more. Notice that a long double takes 12 bytes to store, 12 bytes of memory to store a long double. We used that when we were doing factorials because the numbers got very large. So this is also your most significant digits for accuracy. So let's use a little bit more of that size of function because it's kind of interesting. So size of character is 1 byte. So if I use the size of, and you can see I called the function size of character, it's 1 byte. And an integer, for example, is an int is 4 bytes. Oops, long double is 16 bytes on my machine, although the example I just showed you said it was 12 bytes. So to a certain extent it's machine dependent. It depends on your computer, your microprocessor, how much memory you have. Whether you're a 64-bit machine or a 12 or an 8 or a 32-bit machine, that will influence your answers there. So it might be fun for you to see what you get. Size of is here's the ANSI reference card that I gave everybody on Laulima. So the size of is a function that's associated with all of our data types, and this is a list of data types for ANSI. Notice pointer is listed, but pointer has to be associated with a data type, so I can have a pointer to an int, a pointer to a float, etc. Any of these data types. So that was in your ANSI reference card. Let's look a little bit more about declaring our pointers. Back to the example I had a moment ago. I guess I changed the value that's associated with the variable whose identifier is number. Notice my use of correct terminology there. So the initial value of p number is the address of the variable number. The declaration of number, this line right here, this is the declaration of number. It must precede the declaration of the pointer. Otherwise, the compiler won't know what to do, and you're going to get your code won't compile, and you'll get an error. So you must already have allocated some space in memory for number before you can have a pointer to number, before you can store the address of number. So that makes sense. You have to have a number stored in memory somewhere before you can store the address of that variable. So that order is critical. More examples to help with the understanding here. So in this example, I've declared an int called number, whose variable is, and just to be different, I declared it in hexadecimal. So I said 0xa. A in hexadecimal is the number 10 in decimal. Again, send me an email if you've never seen hexadecimal before, and I will point you to something to help you understand it. So hexadecimal is base 16. Number 10 in decimal is A in hexadecimal. So now I'm going to, next line of code, I'm going to print the address of number, ampersand number. I'm going to print the address of number and a new format specifier that we haven't seen before. I'm going to use the format specifier %p, which corresponds to an address, and this is an address, so that's nice. So this first printf statement gives this answer right here, which I just copied and pasted over. Number's address is, and I get some hexadecimal address right here. Next printf statement says number's value is, and number's value is 10. Straightforward enough. The only thing different here is that this is the first time we're actually looking at addresses in memory. Now I'm going to make a pointer to number. I'm going to call the pointer p number, and it isn't a pointer, so I have to use that address, which says the value of p number is the address of number. And I'm just going to do some proof of that down here in these next 4 printf statements. So first I'm going to print the address of P number. So the address of P number is something different than number. But let me just point out a few things down here. I found up here that number's address is this hex number and it ends in 10. I mean, its value is 10. So I have an address right here of number. It's the address of number, and the value of number is 10. This next thing I said was, what's the address of P number? I said, what's the address of P number? So P number is stored somewhere else in memory. There's P number, and it printed its address right there, correct? But the value stored at P number is the address of number. CAAC, it ends, right? Right there. Correct? Just for the fun of it, I said, what's the size of P number, which is an address, right? Oh, I didn't say what's the size of the address of P number. I said, what's the average size of P number? So P number is an int, which takes 8 bytes on my machine. Yes, no, it takes 4 bytes. Okay, this is the address. Correct. Let me make sure. Sometimes I too can get momentarily confused when I'm dealing with pointers. Yes, I'm literally asking for the size of P number. P number stores an address. I get 8 bytes because I have a 64-bit machine. So 8 times 8 is 64. So that is correct. Sorry, I had that momentary lapse of concentration. P number's value is an address. So P number's value is an address right there. I already showed that. And this last one, using my dereference operator, which I'm going to talk about here in just a second, is it says what's the value that I'm pointing to. So by dereferencing, I'm taking out the addressing factor and I'm seeing what am I actually pointing to, and I am pointing to a number 10. Pay attention to the notation in this example. This is the one that kind of straightens. It's an example to help you keep track of whether I have an address or a value or something pointed to a value. From your textbook, it has good programming practices and programming errors. I am going to point out something about it, just a comment. A few comments. It says the asterisk notation is used to declare pointer variables, and it doesn't distribute to all the variables in the variable declaration. So you have to have an asterisk for each thing that you're making a pointer. So you can't say int asterisk and then have a list of pointers. You have to say int asterisk pointer 1, asterisk pointer 2. So like this example, this is correct if you're declaring more than one pointer. The other thing that has good programming practices, your textbook likes to use PTR in the pointer variable names. I learned C originally from a different textbook. I use P in mine. So your author likes to say X pointer, Y pointer to declare a pointer. I and mine happen to like to use P number, for example, P in front, P prefixing the name that I'm associating with, to indicate a pointer. It's up to you. Whatever style you like is fine, but it is common practice to name a pointer variable with some kind of a name that indicates it's a pointer and tie it to the variable name that it's pointing to. So the asterisk is called an indirection operator, also called a dereferencing operator. I usually call it a dereferencing operator, but either terminology is correct. It returns the value of the object to which it is pointing. So, for example, I've declared an integer called y, a variable called y whose data type is an integer and whose value is a 5. And then I created a pointer to y called y pointer, and I said the value of y pointer is the address of y, which is fine, which is good. And then I said print y pointer, and when I do that, because I'm using this dereferencing operator, the asterisk, it doesn't refer to an address anymore. It refers to the actual value that it's pointing to. That's why we say it's dereferencing, and so it will point to the number 5. These are a few words from your textbook that I'm going to go over a little bit. There are 2 ways to pass arguments to a function. We've already talked about it in my last 2 YouTube, pass by value and pass by reference. When we were doing an array, an array in our function, when our function had an array as a parameter, it was an address that was being passed into the function, which is kind of a pass by reference example. Everything else in C is going to be passed by value. But we're not, when, this is a small technicality, when we have a function whose parameter is an array, notice that we don't actually pass an operator, we don't actually pass an address into the function because we didn't use the ampersand operator. So basically, when we call a function that is looking for an array to be passed to it, we are basically sending the address of the first element of the array. So that's actually what we're sending in. So it's kind of still a pass by value. I have 2 examples coming up to illustrate pass by value and pass by reference to help that be clear. There's another statement in your textbook, which is a little bit wordy right here. Many functions require the ability or the capability to modify the variables that are in the caller, or in other words, in main. So main calls the function, but you want the function to modify the variables in main and not just be something that's local to the scope of the function. We do that when we modify things in an array, and we are going to do that in a moment when we show another example using pointers. But the reason we do this in short, easy words is it's faster to pass an array or pass an address to a function than pass a whole array to a function. That's the bottom line. So in C, we can use pointers and the indirection operator to simulate passing by reference instead. So instead of, because normally when you pass a value to a function, a copy is made of the value. It's then given to the function. The function does its thing and it returns the result. But if you pass an address to the function can operate on the thing that's in the address. And that's what we're going to talk about. So I have 2 examples. I am going to use your textbook examples right now. I am going to create a little program with a function that cubes a number. And in one case, I'm going to make the function work by passing a value to the function, so it's going to be passed by value. And in the other case, I'm going to make the function use a pointer, and in that case I'm going to be giving an address to the function, and the function is going to operate on the address. So that's what I'm going to illustrate. Here's the first example. This should be a program you could whip out pretty quickly. You're used to this by now. Here's my function prototype. It's called cube by value. It expects an integer to be given to it. Cube by value down here. Here's the actual function definition. I have a int as its parameter. I get the value of the int into the function. I cube it and I return the result. Here's my caller program in main. I declare number to be 5. I print the original value of number. And then I call the function, pass the number into the function, which is a 5, cube it, and return the result and assign it back to number. So the value of number has now changed. The value of number is now 125. And then I'm going to print the result. Oops. There's the result. The original value of number is 5. The new value is 125. The new value of number is 125. And this is what we expect. This is what we're used to doing. Now let's do our pass by reference example, which will use a pointer. So here's my function prototype, cube by reference. Its parameter is a pointer. So the pointer, remember, is an address of where a variable that you're going to use is located. Here's the actual function down here, function definition with a pointer. And so in this line of code, I take the thing that I'm pointing to, and extra asterisks here, I'm cubing it, right? So the thing that I'm pointing to times the thing that I'm pointing to times the thing that I'm pointing to. It's all at the same address. And then whatever that calculation result is, I assign it back into that same location with this assignment operator here to a pointer pointing to a certain location where it's stored. So now let's look at my main caller program. I again declare number to be 5. I print the original value of the number. And then I don't reassign number. Instead, I say I'm going to cube the number by reference. And I'm going to pass in the address of number. So I pass in the address of number. It does its operation on it. But it modified the value stored at that address that I'm pointing to. So it modified number in the end outside this program. Modified it in the it's been modified in the caller program versus only being in a function. So now I print the new value of number, and as you expect, the new value of number will be 125. But the function modified the value of number, which was different than what we did before. The function was, in this case, the function was not able to modify the value of number. I had to call the function, get the result, and then reassign it to number. So that's the difference there. You can use a constant qualifier with pointers too, just like you can use it with data. So I have pointer and data. Those are two things. So there must be 4 combinations here. You can have a non-constant pointer to non-constant data, constant pointer to non-constant data. Anyway, there's 4 cases here, 4 ways to pass a pointer to a function. When you declare something constant, oftentimes you're changing the privileges that variable or that pointer has. So it is important for you to remember always to keep the principle of least privilege in mind when you're writing your programs. Don't make something a global variable that everything in the program can see unless it needs to be a global variable. So absolutely don't give any more privileges than is absolutely necessary for your program. So I have a few examples here. You don't need these examples per se for your, you don't need the concept of constant for your programming homework problems right now, but you should be aware that the qualifier constant does exist. I would say that normally, unless it's absolutely necessary, you normally have a non-constant pointer to non-constant data. And this is the first example, and it's a good example. So I have a string of characters, which is an array of characters right here that I want to convert to all uppercase. So we have some character functions that we can use at our disposal. One of them is called toUpper. And to use our character functions, we have to include the C-type in our C-type header in our preprocessor declarations. In my C reference card, if I go to string, well, it's in character operations, the C-type header file. These are all of the different character kind of functions that you have to use to test characters or to work with characters. There is a toLower that converts to lowercase. There is a toUpper that converts to uppercase. You can test if things are a digit. You can test if things are a space. You can test if you have a control character. You can test if it's numeric or if it's an alpha character. You can go to lowercase. So these are all of the different character functions and tests that you have at your disposal if you can include C-type in your preprocessor directives. So that's what I'm going to do. I'm going to convert a string to all uppercase. This is the string or array of characters. It has mixed upper and lowercase and some numbers in it. But then we'll see what happens when we convert everything to uppercase. Program first says the string before conversion is print the string. Then I call this function convert to uppercase. I pass string. Now string is an array, right? I have string is the name of an array. So when I pass string to a function, I'm passing the address of the first element of the array. And then I'm going to print what the string looks like after I call the function. So my function uses pointers. And here it is. Here's the function definition. So the parameter is a pointer. It's a pointer to a string. So I called it string pointer. At first, so I'm going to walk through the string or the array of characters one element at a time, and one element at a time I will raise it to uppercase. If it's already in uppercase, there'll be no change. So that's how I'm going to work it. So I do a while loop and I test that while the thing I'm pointing to, so I'm pointing to the thing that's in the array, the first pass through the while loop, it's the first element of the string of the character array. While it's not a /0, so remember at the end of every string there's a /0 escape sequence. So while I'm not at the end of the string, I am going to raise to uppercase the thing I'm pointing at. So since I have the pointer, the asterisk symbol, I'm going to raise to uppercase the character that that's literally stored in that memory location, or the thing that I'm pointing at. And I'm going to put it back in that same location because that's what it says to do. And then I'm going to go to the next element that I'm pointing to. So make string pointer point to the next character. And I'll go through the whole array and convert everything to uppercase. This is the net result. All the lowercase letters are changed to uppercase, and nothing happens when you go to uppercase with these numeric things. So it worked nicely. The next example is using a non-constant pointer to constant data, and this is how I do my declaration. I say it's a constant. I put the constant qualifier in here, and then what I want to do is print. I have a string of characters right here, or an array of characters, and I just want to use a function to print the string. So my string is not being changed in any way, shape, or form. I'm just printing it out, which works fine because it is a constant and I can't do anything with it. I cannot attempt to change it. If I try to change anything, I will not be able to change anything. So I just say while I'm not at the end of the string character, I am going to print each character one at a time. No problem. So this example, you attempt to modify a constant pointer with non-constant data. So I declare two variables x and y right here, and then I try to make a constant pointer out of the address of x. Which is fine. So that's allowed. I can put 7 in that value because the pointer is not actually what's constant, but the pointer is what's constant. It always points to the same memory location, but the variable x is not constant. So I can change the value of what I store at where I'm pointing, but I cannot assign an address to pointer because the pointer is constant. Okay, so the next example I have is using a swap function and doing it with pointers. You've been exposed to swapping the swap function in an earlier chapter, but now I'm going to do it with pointers. My example is a little bit different than the example in your textbook. Your textbook creates a swap function, but it swaps elements within an array. So there's an added level of complexity to the swap function defined in your textbook versus I'm just going to swap the values of two variables. Like I'm going to swap the value of C and D. Right now C is 3, D is 5, and I'm going to swap it by calling the swap function, and I'm going to use pointers to do it, versus swapping elements of an array. But I think you have to understand what's happening in the swap function with pointers before you have to extend it to the array. So that's what I'm going to do. So I have a variable C declared and D declared. C is 3, D has value of 5. I make a pointer to the address of C and a pointer to the address of D. And then I'm going to call this is my swap function prototype, which has pointers as parameters, pointers that are pointing to integer values stored somewhere. I'll call the swap function. When I'm calling the swap function, what is being passed right here? What is pointer C and pointer D? What is being passed? This is an address being passed. Refer back to this example that I did a little while ago with this variable called p number. So this third printf statement shows me an address. The value of p number is an address. It happens to be the address of where something is stored. So let's go back now to where I was at, my swap function. Oh, there I am, swap function. So this is an address. And because I have a pointer here as a parameter, I'm expecting to get an address passed to it. So I pass the address of C, pass the address of D into this function, and what does this function do? So I'm passing an address, but it's going to operate on the thing pointed to. So I have to create a temporary location first, and then I say get the thing that I'm pointing to, which it happens to be in this case because I called pointer C. I'm pointing to the value of C. Get the 3, store it in temp, then get the 5, store it in the location of where C is. It's a little confusing, to that location, and then get the value that was stored in temp and put it back in the B location. So A was stored, something was stored from the A, and it was brought back out and put in B. So let me make a few notes on here with my pen. So this is an address. I'm passing an address right here. And this means it is a pointer to contents of an address. So that's the difference here. This is point to the contents of an address, but I have to give an address to the function for it to work. So there's an address of where the variable is located. The address the example in your book is in section 712 on page 309, and they have a swap function that's swapping elements of an array. It's actually very similar, little wordier variable names, which is fine. I was trying to keep it so you could see what was happening without being lost in too much text. It's part of a sorting algorithm, the example in your textbook. It's a pretty long program. Our first assignment with pointers, I'm going to keep your homework simple so that you get the concept of a pointer before being overwhelmed with bigger expectations out of a program. You can also do math with pointers. So I can increment an address, I can increment, I can decrement, I can add numbers to pointer, which moves things around, points to different places in memories, and you can compare pointers, which are addresses, right? But you can only do it within the same array. So let's start with a simpler example first. I have an array of characters. Here it is, A, C, B, D, E, F, G. And the reason those two A, B, C is out of order right there is for the next example after this slide. And then I make a pointer to my message array. And I just call it P. I should have called it P message, but I'm trying to minimize how much text I'm showing here. So it's a pointer to the message. So my first printf statement, I say, what's the address of message element 4? So message element 4, 0, 1, 2. Oh, that's the first element. Oh, 0, 1, 2, 3, 4. The address of the character E. So no big deal. I print out the address of character right here, E, right there, and it has an address. I used a %x format specifier, so I get that in hexadecimal. My next line of code says that I want to see the address, because P is an address, address plus 3. So if it's just an address. P is just an address. It happens to be the address of where this array starts, but P is just an address. So if I print out the value of P plus 3, I get an address. Notice that it is one address before this address. So this was the fourth element in the array, and this is the third element in the array because it's P plus 3. And I just am printing out an address. Not very exciting. My third printf statement says print to the thing I'm pointing to at message plus 3. Well, message, message is an array, so message, whoops, how did I get that? I hope I don't have a mess up here. I got that funny thing up there and then my recording stopped. Hopefully I'm okay. So message is the same as, say, oh, I just did it. Sorry for those little blips. But message, when I use it in this context, is the same as saying address of message element 0. So, because it's an array. When I'm using an array and I call the array's name, it's the same as saying the address of message element 0, or where the array starts in memory. So I say, what is the value of the thing that this address plus 3 is pointing to? So the beginning address plus 3. So beginning address plus 1, 2, 3 is a D. And so the value of the thing that I'm pointing to is D, and that's what the next line of code shows. I did this example because it's a simple example, because my next example is more complex looking. So I'm going to spend a few minutes with this next example. So here I've declared an array of long integers, and when I specify that array I have to put an L after the end, 15L, 25L. So it's 15, 25, 35, 45, but they are specified as long ints, which takes more space in memory. Actually it takes 8 bytes to store a long int. Then I make a pointer to that array. So that's really a pointer. I could have alternatively written star P equals ampersand multiple element 0. It's the same meaning. I'm pointing to the beginning of the array. And then I need an I for my iterator here. And then I'm just going to do a for loop, but my for loop is basically going to give out some information. I'm going to say the address at pointer plus 0, so it's the beginning of the array, which is the same as saying ampersand multiple element 0. I'm going to give the address. It happens to be given in decimal, and then I'm going to say, this is just a space. Then I'm going to say, what am I pointing to? So there's my dereferencing operator, address plus 0, and I'm going to give what the value is. So let's look at my for loop here, because a few things are happening. The control statement here, let's come back to it in a moment, but just let's look at one at a time what's happening. So I need to go through this for loop 4 times. So I is going to be 0, 1, 2, 3. So I said address of, the first thing I'm wanting to do is, what is the address of, this is just information to the user, right? Address of P plus 0, looking at my yellow, which is the same as saying ampersand multiple element, so address of multiple element 0. So this is just formatting stuff. So there's where there's my green. Then I have a colon, prints the colon, and then here's where it gets more interesting. I have unsigned long P plus I. So P is an address. 0 on my I is 0 on my first pass through this loop, for this for loop. So it's going to print out an address right here, right? And there's the format specifier for printing out the address. I used a %LLU so that I get the address in unsigned int rather than in hexadecimal. So that's what's happening here, but P is an address. And then I want to just say, this is text to the user right here, P plus whatever I is, its value is. So at that point I'm saying, what am I pointing to? Here's my dereferencing operator. Print me the thing that I'm pointing to at P plus I. So the starting address plus 0. Print me the thing that I'm pointing to. And it happens to be a 15. There it is in the output of this program. So kind of a lot of things happening in this example. Let's look also how I managed to go through the loop 4 times, because this is kind of interesting using the size of function. So I said size of multiple, but multiple, this array was declared as unsigned, or long ints, sorry, long ints. And so each value is going to take up 8 bytes. So I don't want to just go through the loop by size of multiple, because that would be 32 times I will go through the loop. 8, 16, 24, 32 times I would go through the loop. So what I did was say size of multiple, which the answer will be 32, divided by the size of multiple element 0. So it'll be divided by 8, because each element takes 8 bytes. So that way I can go use the size of function to determine how many times to go through the loop to go through the whole array without actually having to declare some constant size equals 4. Or this is also a good way if my array size varies, or I don't know the array size, I can use this size of type operation to know how many times to go through a loop when I don't know the size of the array. And that will happen when we start doing file input and output. You will not know the size of your array necessarily that you're reading into your program, and you can use this size of functions to accommodate that. So looking at what's happening in memory, and I could call this the memory map. At the first address I'm storing the value 15, and 8 bytes later I'm storing the value 25, and 16, and then 16 from the start I'm storing the value 35, and the value of P is the address of the beginning of the array. Correct? So the address of P, the P is the pointer to the P is the pointer to the beginning of multiple, so the value stored at P is this, which is the start of the array right there. P has its own address. I don't know what it is. I didn't write it in there, but P has its own address. So pointers in array have kind of a very tied together relationship to each other in the C language, and sometimes they're often used interchangeably. When you're dealing with an array, it has a starting address. So the array name can be thought of as a constant pointer. Okay, so I'm going to stop this YouTube right here because it's at 50 minutes. The next YouTube I'm going to talk about two-dimensional arrays, and I'm going to do some examples, more examples that show the order of things showing in memory. Okay, bye now.